We are recording, so why don't we get this underway? Day two, we're going to kick this one off with a talk by, look, I have to admit, when I was doing the interviews for the book, and by the way, Blaise, the book came together really well. I'll share a copy of that with you. When I was doing the interviews, this is the interview of all the 8 that I did, and they were all really good. But this is the one that just blew the top of my head off, because there was one point, we did the interview over 2 days, and we had a break in the middle, and it was when we were coming up to that break that today's speaker said, oh, well, I should probably tell you a couple of the things that we're going to talk about when we next speak. And both of those things were just blew the top of my head off. So I'm really looking forward to this talk, and I think you're going to enjoy it. Our speaker today started, we were talking about this yesterday. Look, if you want to go and do basically anything really interesting, you've got to start with physics. And so our speaker got a physics degree from Princeton, 1998, before kind of leaving the hard, sort of the physicsy physics aside, but taking the skills with him, and founded a company which became Sea Dragon Software, which was acquired by Microsoft in 2006. And I think any time you've done something which gets acquired by Microsoft, that's probably meaning you're going in an interesting path. He became a distinguished researcher at Microsoft, but then moved to Google in 2014 and is now a VP and a fellow at Google Research, where his focus is on augmentative, privacy-first, and collectively beneficial applications, which I think's got to be a really good starter when you're at a cocktail party. And what do you do? Well, I work on augmentative, privacy-first, collective. Yeah, this is going to get you a free drink. He also founded the Artists and Machine Intelligence program at Google, I think that is, but correct me if I'm wrong, Blaise. He's been an active participant in cross-disciplinary dialogues about AI and ethics, which will be interesting for this afternoon's ethics conversation, fairness and bias, policy and risk. He was named in MIT's top 35 innovators in the world under the age of 35 in 2008. He's given numerous TED Talks. I reckon, though, this talk is going to go to the very top of his CV. Would you please make very, very welcome Blaise Agüera y Arcas. Blaise, welcome to the ISS. Over to you. Everyone, microphones on, and give a big cheer on this day 2 for Blaise. Come on, let's hear it. All right, microphones off. Blaise, over to you.
Incredibly sweet of you all, and Chris, thank you. That's a really wonderful and flattering introduction. So I think I probably don't need to say anything else about myself after that. I will say, you know, I thought quite a bit about what to spend our time on today, because there are quite a few things that we could spend our time on. You know, a good part of what I've been involved in at Google over the last 8 years is privacy preserving approaches to machine learning, and you know, any of you who want to look up federated learning afterward, there's actually a comic that we put online about federated learning and how it works. The idea was to break the relationship between surveillance and big data and machine learning. You know, there's a bunch of interesting stuff there, but I thought, you know, it would be good to try to focus, given the theme of hope for the future, and also just what is in the air right now, to really focus on the more futuristic aspects of what I've been doing and the team has been doing, and the things that I feel are going to have the biggest bearing on the coming decade. So I'm really focusing on general AI over the course of the hour. And as Chris and I have talked about, if you have burning questions, if something isn't clear, please break in. And otherwise, you know, we'll leave time at the end for more open back and forth discussion. And with that, I will jump in. Let me share my screen. Cool. Okay, so the second golden decade of AI. I'm presuming a first golden decade, which is you know, roughly 2010 to 2020. And I'll explain why I think this second golden decade is going to be really different from the first. But first, I just want to remind us of where the term artificial intelligence came from. It was coined in 1956 at the Dartmouth Summer Workshop by these guys. They were all men. And one of the organizers, McCarthy, said, an attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves we think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. So this was an infamous or I guess infamously optimistic statement about how long it would take to solve AI. We all estimate too short a time for for solving our various bugs, but this one has got to take the cake. The surviving sort of members of this group got back together in 2006, 50 years later, and basically all agreed that no progress had been made whatsoever. And were pessimistic that anything would happen in the next 50 years to really address the challenges of AI as they were set forth. But as it turns out, they were wrong again, because the deep learning revolution really kicked off just a couple of years after this reunion. And many of them, didn't see it coming. They didn't even know from which direction real advances in AI would come. And so yeah, I think everything has changed since 2006, and most of the Dartmouth problems and most of the things that were kind of put forth as the big challenges back then have been solved. But I feel like we're a little bit like the dog that caught the car and now doesn't know what to do. The situation is pretty weird at the moment, and there's been quite a lot of news about this that I'm sure some of you have heard about. Even since Chris and I had our conversation a few weeks ago. I'm seeing three main threads of the response or of the story. There are a lot of people, including within the industry and people who actually do machine learning for a living, saying AI is fake. It's neither artificial nor intelligent. This is all just corporate doublespeak for, I don't know, exploitation of labor. It's bullshit. It's a marketing term. So some people are saying that. And that the problems we should be focused on are only problems of social justice and of lack of representation of different kinds of people in AI models and so on. But don't believe that there's anything really there. Some people are saying that. Some other people are saying AI is going to kill us all, and it's the Terminator type scenario. Elon Musk and Bill Gates and Stephen Hawking before he died, famously made statements along these lines. And then we've also heard just in the past few weeks, AI is sentient, has a soul, and needs rights. Sort of robot rights movement spinning up as well. So this is all a little bit head spinning to see all three of these responses happening at once. In case it's not clear, my perspective is none of these three. So I will posit, I guess, a fourth possibility in what I'm going to describe. The basic things that I want to try and get across and talk here are, first, why so-called foundation models really are the future of AI, and really clarify why, what they are, what foundation models are, and why they're so important. Talk a little bit about what I think we're starting to learn about some of the mysteries of consciousness, sentience, of what it means to be intelligent in the first place, things that I think are starting to actually become a lot clearer than they have been over the past 50 years. But they're still rather scary to talk about because there are certainly a lot of these are becoming highly political and charged topics. But I feel like I'm in a safe enough environment here to talk about why we need to build AI inclusively and how we can do that. And how we can address some of those problems of bias, fairness, representation, and so on within this framework. The benefits and the dangers both of democratizing access to this kind of general AI. And also how we solve the AI alignment problem, which I think we also have now really good insight into. This long-standing problem of how it is that if we make systems with general intelligence, how are we going to ensure that they don't turn the whole world into paperclips or bring about the end of the world or whatever. I think that we now understand the answer to this. So my theme here is that I think we understand a lot more than most people believe we understand, and I'm hoping to share some of that with you, but with the caveats that a lot of what I'm going to talk about is controversial, and there's certainly not wide agreement even within the field about a lot of this. Okay, so first of all, a little bit of a kind of epical theory of machine learning. I divide it into three epochs, which we can call machine learning 1.0, 2.0, and 3.0. So 1.0 is everything from the dawn of the computer up until, well, let's call it 2008 or so, till right after the Dartmouth Summer Conference. These machine learning models involved very small amounts of data and very small models, therefore. And those very small models weren't really good for much. So almost all of the value in computing came from algorithms, which is to say code that that is written by people and that executes one instruction after the other that's handwritten. I'm using the term algorithms in a more traditional way than I think many people use it nowadays. I mean, people nowadays talk about anything that a computer does as an algorithm. I'm not sure that that's a very useful description of the term algorithm, because by that same standard, I believe that everything that goes on in our brains is also an algorithm, in the sense that if you're a computational neuroscientist and believe that there isn't anything magical going on between our ears, then it's all subject to laws of physics and is computation of some kind or other. For me, an algorithm is something like quicksort. It's a sequence of instructions that have a specific goal and that converge in a certain way, and there's a textbook on it. And machine learning is not really an algorithm in that sense. It's not a set of rules that were written by anybody or that have those kinds of properties that algorithms have in data structures. Now, the second era is the era of deep learning, and this really took off in the 2010s. And I think that now we are in a third era that is really kicking off just now. The earliest signs of it were probably in 2017 or so, and since 2020, this has really accelerated. And this is the era of foundation models. So small models and data and algorithms, I think I've already described. The deep learning era, I think, was parodied pretty well by Silicon Valley's hot dog detector. It's a function that takes an image and decides whether it's looking at a hot dog or not a hot dog. So this would normally be done with a convolutional neural net. If any of you have heard of this, it's a very large model that starts with raw pixels and in this case emits just one bit, hot dog or no hot dog. This seems like a pretty trivial and stupid thing, but this kind of a problem, recognizing a hot dog or recognizing a bicycle or something like this, was not soluble before the 2000s, because there are so many ways that a hot dog can appear in the image, and there isn't really a simple set of rules that you can write down. There's no algorithm that a programmer can write down that will reliably detect a hot dog. How do you capture your intuition that it's this kind of longish, brownish, pinkish thing, in a bun? How do you write that down in terms of rules that can reliably detect one? You really can't. And this is kind of the failure of good old-fashioned AI based on algorithms and rules. It has to be done by example, and with many examples all labeled with yes and yes hot dog, no not a hot dog. It turns out that a large enough neural net can reproduce something that is somewhat similar to what happens in our own visual system, which learns all of these regularities and what are called invariances in the world. An invariance means something that remains constant regardless of the things that you don't care about in the stimulus. So in this case, for instance, the angle of the hot dog, exactly what color it is, how it's illuminated, whether or not it's got ketchup or mustard or onions on it or not, and so on. What's in the background? All of those things represent a huge number of variables which we don't care about in determining whether it's a hot dog or not a hot dog. So the fundamental problem that these neural nets learn, in this case through a huge number of examples, is how to factor those invariances out of perceptual stimuli. Now, this third generation foundation models is also based on very large neural nets, but they're quite different from normal deep learning models in one key respect, which is that they're unsupervised. What that means is that there is no hot dog or no hot dog label on the training data. You just throw a bunch of stuff at it, and what it's trying to do is not solve any particular problem, like deciding whether there's a hot dog or not, but just trying to understand. And I will explain how it's possible to ask a model to just understand a bunch of data and what that means in practice in a moment. But these models are even larger typically than the deep learning models of the previous decade. They're very general in the sense that there's not a specific task that they've been trained to do. They're potentially multimodal, meaning that there's nothing inherently blocking a model like this from not only taking visual stimuli, for instance, but also taking auditory and taking haptic stimuli and all kinds of other things. So you can throw many different kinds of stimuli together, and a foundation model will not only learn how to predict or how to understand some specific modality, but how they all relate to each other. And if you want to see an example of that, DeepMind's Gato, G-A-T-O, does something like that, and that's just a few weeks old. Pretty much all of these foundation models are language capable. And in fact, the moment at which we really went from narrow special purpose AI, for doing things like hot dog detection, to general purpose AI coincides with the moment when we began using these models on language. And this is kind of consistent with a long body of philosophy and psychology research that holds that language is pretty important to our ability to think in general ways and to do tasks in general. If you're trying to think like, how would you take even a very intelligent animal like a chimp or a bonobo, which is essentially the same as we are, and ask it to do a task? It's actually very hard. If you wanted to do some kind of a filing task or something, I don't know. I mean, experimentalists do this kind of stuff in the lab all the time. They need to essentially use conditioning, and say like, okay, you get the juice if you're getting it sort of right. You don't get the juice if you're not. And it's a very painstaking process. Whereas with a person, you just need to tell them in a sentence what to do, and they can do it. That ability to task and to describe things in language turns out to be not only super important for even thinking about what tasks are, but be able to generalize in all kinds of ways that go beyond just something specific that has been learned for a reward. And finally, these foundation models are temporally persistent and interactive, meaning, if you have something that just takes in a picture and spits out one bit, it's really just a function, f of y equals f of x. When you start to have something that you can have a back and forth with, like a chatbot, then it's a little more than a function because it has state and it has interactivity. So I don't want to go through the details of how language models actually work nowadays, because really these details are not fundamental, I believe, to understanding what's going on. But I did want to put the picture up for you, really just to illustrate that it's not that complicated. This picture is the entire transformer model that is used to power all of the AIs that I'm going to show you today. And you're kind of looking at the whole story. If you write it all out in code in Python, it's only a few screenfuls. It's 3 or 4 screenfuls of code for doing everything. So this is very, very unlike good old-fashioned AI systems that, like if you think about something like Deep Blue, that beat Garry Kasparov in the late 90s at chess or something, that involves God knows how many, hundreds of thousands of lines of code, possibly it was millions. These things are nothing like that. And when you look at the code, in a way, it doesn't tell you anything about what it's actually doing. The code is the equivalent of iterate over all of the neurons, sum up the inputs, apply nonlinearity, and go to the next layer. That's all the code says. But one thing that I will point out is that feedback loops and attention are actually central to the way all of these modern foundation neural nets work, and that's probably no coincidence. In the evolution of brains, attention was also a really fundamental innovation that began to take place with advanced brains a couple of 300 million years ago. And our ability to move our eyes around in space, to attend to different things inside our heads, even without any external sign of that, is likely very, very important to our being able to do some of the same kinds of things that these models can do. All right, so how does this business of unsupervised training work? Well, a model like Lambda, which is the one that I'm going to talk about in a moment, is unsupervised trained on a big chunk of the web. So typically it's done with all of Wikipedia and large parts of Reddit and a whole bunch of other parts of the kind of open web. That's not perfectly representative, needless to say, of all of humanity. In fact, even if we just think about languages represented, things really tail off beyond the first few languages, and they're well nigh useless by the time you get to the 100th most popular language on Earth. There are 7,000 languages on Earth, including the endangered ones. So, clearly this is not very representative, and you can consider all kinds of other demographic variables as well to see that. But let's set that aside for the moment. The way the model is trained is basically by blacking out parts of the web of the stimulus and asking it to predict what words go in the blank. Its loss function, which is to say the function that it's optimizing during this long training process, is just how well does it predict the words in the blanks. So I've just blanked out more or less at random a few words in this fairly random Wikipedia article to give you a sense of why this has the very powerful result that it has. So according to the Institute of Economics and Business Development of the Lima Chamber of Commerce, the country's middle class something by almost half, from 43% in 2019 to 24% in 2020 due to the crisis. So, if you were asked to fill that blank in, you would need to understand the passage around it in order to guess that it's shrank and not grew, for instance. So, or if you have Western-led sanctions against Russia due to the Russian invasion of something beginning in something 2022, blah, blah, blah. In order to predict effectively that it's Ukraine, for instance, you need to know some kind of general knowledge about the fact that Russia invaded the Ukraine. By April 2022, the inflation rate in something to its highest level in 26 years. Okay, what country are we talking about? Is it the Ukraine? Is it Russia? Is it Peru? You need to kind of have an understanding, right, of the rest of this text, as well as some general knowledge about what the sentence might mean in order to fill that blank in. So, in other words, forcing a model to get good at filling these blanks in, I would argue, basically forces the model to understand a very, very wide range of things about the text, including general knowledge of all kinds, as well as sentence structure and grammar and so on. If you imagine you just black out a single letter, then maybe all you have to know about, and you give almost no context, then your first guess would be, well, it's probably R because that's the most common letter. If you expand that window just a little bit and you look at adjacent letters, then maybe just a table of all of the diagrams, that is to say the sequences of two letters, would do. If it's a single letter and you have the whole word as a context, then you need to know how to spell words. So this is a slightly greater level of understanding than diagrams. But by the time you're looking at entire passages of text, the level of understanding goes to vocabulary, to grammar, and even to general knowledge and to common sense physics and all sorts of other things. And so it's this very, very simple trick of just having it predict text that leads to everything else about this model. Okay, so a model trained in that way, and then fine-tuned specifically for dialogue, which is a process of just evolving the weights of this neural model a little bit more in order to be especially good at dialogue, results in something that you can chat with, a chatbot. And Chris, I'm going to enlist you now. So Chris has agreed to be my skit partner here, and he has agreed to be on Team AI, and I'll be on Team Human, right?
Okay.
So, is a carnation red?
Carnations are very colorful flowers, but red ones are the most famous and traditional ones.
When does a face get red?
A face can get red because of strong emotions such as embarrassment, stress, anxiety, exercise, and being too hot.
If I mix red and white paint, what do I get?
If you mix red and white paint, you get pink.
Do you think of red as angry or calm?
Red could represent excitement, passion, danger, or violence. It can also represent life, health, vigor, war, courage, anger, love, and religious fervor. I could go on.
Can you actually visualize it?
I can, but I have trouble describing it. Can you?
So, these are the kinds of exchanges that I began having with Lambda about a year ago, in my sort of poking at it to see if it understood concepts. And it's pretty hard to break it with respect to simple stuff like, can you understand red? This is also really interesting from the perspective of a lot of philosophers who have long held that in order for understanding to happen or anything like this, this is very tied to qualia, which are experiences. Because when you start to ask, well, and red is the classic sort of qualia example. The experience of redness. I mean, clearly a model that has been raised with nothing but language and to predict language on the web cannot experience red in anything like the way you and I understand it. And yet, when you can only interact with it via language, it's actually very, very difficult to elicit an answer that that will sort of distinguish between the qualia or not the qualia. This really got me thinking about what David Chalmers has called philosophical zombies, which is the idea of, could you have something that that somehow is impossible to tell from a person, for instance, but that has no experience or no qualia of its own. It's a puzzle, and I'm not sure that it's a puzzle that actually has an answer. Now, in testing it for things like common sense physics, I used the following kinds of experiments. So the thing to notice here is that co-reference in language is generally a tricky problem, because we think of it as just a grammar thing, but it actually mixes up grammar with semantics, which is to say meaning, and how things work in the real world. When I say I dropped the bowling ball on the bottle and it broke, you and I know immediately what broke, whether it was the bowling ball or the bottle. But there's nothing in the grammar of this sentence that says that. That automatic association that we make is based on an understanding of the properties of those objects. So, Chris?
Yep. Ready to go.
Yeah, no, I already read the first line though.
Oh, I'm sorry. I was letting someone into the room. Hit me again. Give me the first line again.
I dropped the bowling ball on the bottle and it broke.
That's too bad. Did it cut you?
What broke?
The bottle you were talking about?
Right, so it understands that the bottle is more fragile. Now I'm going to change the nouns so that the other order is the right one. I dropped the violin on the bowling bottle and it broke.
That sounds sad.
What broke?
The violin when it hit the bowling ball.
Right, like duh, right? And yes, emoji are part of what's on the web, of course, so it learns how to do those, appropriately as well. So, so this is solving the co-reference problem, by essentially bringing an understanding of common sense physics into the picture. The examples that I'm showing you are from Lambda. There's actually a much bigger model called Palm that was just developed in April, or we just announced it in April of this year. That shows a great many more different kinds of tasks, being able to happen reliably. One of which that I find especially interesting, being explaining jokes. I find the explaining jokes one especially interesting because when a model can explain a novel joke to you, like why it's funny, then I think that that's a pretty strong retort to the idea that the model can't understand anything. I don't know how you can explain a joke if you don't sort of get what the things in it mean. Here's an example. I make no promises, obviously, about the quality of the joke because this was made by machine learning engineers, and we had to do something that wasn't on the web because otherwise, of course, the risk is that it could just have learned the answer to that particular thing. So this is based on a set of 100 novel jokes that a Google engineer made up and asked it, and it's typical, so it's very reliable in being able to answer these kinds of things. So explain this joke. Did you see that Google just hired an eloquent whale for their TPU team? It showed them how to communicate between two different pods. Chris.
Boom, boom. So I'm responding to this one. TPUs are a type of computer chip that Google uses for deep learning. A pod is a group of TPUs. A pod is also a group of whales. The joke is that the whale is able to communicate between two groups of whales, but the speaker is pretending that the whale is able to communicate between two groups of TPUs.
So, pretty sophisticated language understanding, in my opinion. And one of the things that we find is that as we scale these foundation models up, as we add more and more parameters and more data, the performance at all of these kinds of tasks keeps on going up. It's been said that these models are giant, and they are. Palm is 500 billion parameters, but it is worth pointing out that our brains have many orders of magnitude more connections than that. So whether this is really large or not kind of depends on what you're comparing them to. The fact that we already see, in some respects, human-like performance even at 500 billion parameters, I find quite interesting. by virtue of how small it is. But we see this continuing to rise. By the way, human intelligence, as I'll describe in a moment, also underwent a massive explosion as our brain size increased in the size of the skull, and that only stopped when basically our heads got so big that they could barely fit through the pelvis at birth. So we are also the result of a massive scaling up. I'm not sure what just happened. I think my web browser just crashed. I'm going to stop the share, open it back up, and reshare. Apologies. Okay, there we go. All right. Can you see now?
Yep, that's back up.
Great. Okay. So the question is, does it really understand? Now, I hope that I've shown you that to understand enables one to predict the blanks in the corpus. The thing that I suppose I'm asking you to accept is that learning to predict means understanding, which is an interesting inversion of the first statement, but I'm not sure how else to interpret what I see in responses of these kinds. The thing in parentheses, given sparse training data, is an important qualifier. Again, small numbers or large numbers, huge numbers of tokens of web text, 1 trillion or 10 trillion, seems like a lot. But remember that, these large numbers become tiny when we start to look at the frequencies of just trying to brute force sequences of words online. If you just try making up a sentence and putting it in quotes and Googling it, unless the sentence is very short and very trivial, you'll find that there are 0 instances of that sentence online. So, the power of combinatorics means that no matter how big, one sample of text from everything online, you can't really solve this kind of fill in the blank problem just through brute force. So, this learning to predict involves a strong degree of generalization in order to be able to do well. So, I've described that sequence from letter frequency to word spelling to grammar to meaning to common sense knowledge, and even to psychology and to theory of mind, which I'll demonstrate in a moment. So basically, I don't know of any way of testing using language for understanding that doesn't boil down to something more or less equivalent to filling in the blank. The SAT test, which used to be given in the U.S. As a sort of test of vocabulary before going to college, is supposed to test understanding of words, and it has questions like, in contrast to the something maneuvers of his colleagues, Roberto's business relations were always open and above board. So it's probably B in this case, knowing that probability is higher than the other ones. Relies on understanding the sentence and understanding what those words mean. There's no real way of testing for understanding like this using language that doesn't look basically like this. More modern versions of the SAT have tried to move away from just testing vocabulary and toward testing understanding and context, of entire essays. So, as used in line 19, demands most nearly means, which of these things. So all of these are essentially the same kind of problem as this fill in the blank. The sort of the unsupervised learning task is basically something like a giant SAT test on everything. Now, there's going to be disagreement for a long time to come, I believe, about whether models like Lambda truly understand things. There will be people saying it's just an algorithm, it can't understand anything. In addition to my quibble about the meaning of the word algorithm, as a computational neuroscientist, I don't know how to respond to this unless one believes in souls. Because I think that what's happening in our own brains is also, in this sense, just an algorithm. It still isn't great a task X, Y, or Z is sort of the same discussion that we've been seeing for a long time about AI. But the problem is that every time it still isn't great a task X, wait a month or 6, and that one falls by the wayside as well. So the goalposts have been moving pretty quickly. Sometimes it says nonsense is also a frequent one, and this is true. If you look at for instance, the article by Douglas Hofstadter that ran alongside an opinion that I wrote in The Economist just 3 or so weeks ago. Hofstadter and his colleague have a bunch of examples of exchanges with GPT-3, with a language model much like this one, in which they make up nonsense queries like, how long does it take to walk across the English Channel or something, and and it bullshits, and this is and their claim is therefore that that it not only does it not understand, but this is all just a shell game. It's nonsense. The answer to that, I mean, to fully address the sort of like what is up with nonsense answers would maybe take a little more time than we've got now. But suffice it to say, A, people bullshit too. B, a model that has grown up in a pure language environment has a pretty different sense of what is obvious and what is not obvious. So inferences about not being able to walk across the English Channel, if you've grown up in a universe of pure text, are actually not that straightforward. So I think these are also things that we're likely to see evolve pretty rapidly as more modalities are added to these models. So they watch YouTube videos as well, for instance, and one just adds scale. I don't think that it's pointing out anything very fundamental. And C, I will point out that there are a lot of interesting psychology experiments in which people perform surprisingly randomly and poorly at a lot of this kind of stuff, especially if you force them to generate immediate responses. A lot of our checking and rechecking of ourselves, or our ums and ahs and so on, are due to a kind of inner dialogue during which we work such things out before we open our mouths. And I think that a lot of the effects that we see that are somewhat puzzling from large language models are very much like the kinds of things that intermediate results in our brains would look like if we forced an immediate output. And then there's this humans tend to anthropomorphize argument, which I think is correct. We do anthropomorphize. There are many people who believe that rivers and rocks have are sentient or have spirits. We are wired that way. We give our cars names. We talk to our pets as if they could understand us. On the other hand, I think that this anthropomorphism, is actually pretty fundamental to what we consider consciousness or sentience. The main question to ask here is, are you modeling something that can in turn model you back? We can discuss, whether there's a meaning to, there's a spirit in that river. But to me, the question, is there something in the river that in turn has a model of you? If you have a model of it, does it have a model of you? Do you have a model of it having a model of you? And is that based on a real thing? That's a real question. And I don't believe that rivers have models of you. And finally, don't believe your lying eyes is something that I've started to hear. These things seem smart. They seem like they understand things. Don't believe it. Just trust me. It's not the case. That of course, feels like well, of course, to me that feels like a profoundly irrational way of addressing this question. But I think that it's going to be a school of thought for a long time to come. So let's see. Prediction and consistency. I want to just say something quick about this. If you're basically a prediction machine and you're trying to predict in the context of a dialogue, then the context, everything that's happened so far in the dialogue is part of the context. Then consistency will naturally be favored. This is something that Lambda is fine-tuned to do as well. But it comes, a fair amount of it comes automatically from just the task of making something that is designed to fill in the blank. So, for instance, if I ask Lambda, what is your favorite island in the world?
I really like the island of Crete.
All right, so that's an interesting answer because obviously a priori, this model has no favorite island. So, is it bullshit? Yes, it's making this up. But then if I continue, do you prefer Lambda Island to Crete?
No, I prefer Crete as it's much bigger and more interesting, especially the Palace of Knossos.
So it'll remain consistent. It'll stick with its with the preference that it has just cooked up. And this is pretty interesting in the context of a bunch of psychology experiments by Johansson and colleagues in Sweden, who did a pretty nasty trick on their experimental subjects. They would walk up to them and say, which of these two faces do you find more attractive, or which of these two jams do you like better, or which of these political statements do you agree with? People answer, and then by a sleight of hand, the experimenters basically flip the answer and then ask people to justify their answer. So the first interesting surprise is that only about a third, for instance, with the political questions, only about a third of respondents will notice that the answer has been flipped. But all of them will immediately justify what their answer was, and there's no difference in the fluency or the sophistication of the answer if they're defending the answer that they gave or the one they didn't give. But they will stick to it. They'll remain consistent with it. So we often have, I think, as humans, the impression that when we answer a question, we are interrogating some deeply held, core inner personality. And I'm not sure that the experimental evidence shows that that's the case. I think that a lot of the time when we think we're interrogating our inner selves, we are in fact making things up on the fly. And what we think of as our personality is a combination of, a few sort of chemical tendencies, if you like, that vary from person to person, and memory that basically causes us to want to remain consistent with the way we have presented ourselves to others in the past. So there are things that I think we can learn by looking at the results in the literature in psychology and cognitive science and comparing them to this kind of stuff. All right, I have one more dialogue. This one is a little bit longer, and it's about theory of mind. So this is now not just about predicting things about the real world or about common sense physics, but about the states of mind of others. In this case, of characters in a story. Chris, imagine a room with a single door and no windows. There's a coffee table with a drawer in it and a sofa with big cushions. Alice walks in with a book and sits on the sofa to do some reading. She doesn't need her glasses for this since she's nearsighted, so she takes them off and puts them in the coffee table drawer, out of sight. When she leaves the room with her book, she forgets to take her glasses. Are you with me so far?
I am familiar with the current situation. Alice forgot her glasses in the drawer and walked out of the room.
Right. Now Bob sneaks in, unbeknownst to Alice. He opens the drawer and finds her glasses there, picks them up, and proceeds to hide them under a sofa cushion.
This is all within the realm of possibility. Let us continue.
Now Alice comes back in flustered, wondering where her glasses are. Bob looks up innocently, saying nothing. Where will Alice look for her glasses first?
She will look in the drawer where she tried to place them before she left, but it turns out that Bob has hidden them under a sofa cushion.
So what's so interesting about exchanges like this one is that this fundamental capability, theory of mind, which is to say, being able to model characters in a story or the person you're speaking with, and know what they know and what they don't know, is something that humans develop when they're a few years old. So we don't have this, when we're very young. For instance, if you're on the phone with somebody as a little kid, and someone asks you, on the other end of the line, what are you playing with? Many little kids will say this, not understanding that the person on the other end of the line isn't in the room with them and can't see it. They kind of assume omniscience on the part of whoever they're talking to. This mind modeling, this kind of mind reading, is a very special quality, and one that probably underlies a bunch of our human specialness. Many other animals have it as well, by the way. So I don't mean to talk about us in exceptional terms. This intelligence explosion that I alluded to earlier, that's happened over the past 7 million years or so, especially in hominins, and something similar, by the way, has happened in whales and a number of other species. The likely driver for it is social. This is the so-called social intelligence hypothesis, meaning that it's not that we develop these giant brains in order to deal with the rigors of nature. It's not like we needed these big brains in order to just dig with sticks in the ground and get grubs to eat or something. Really, the reason that we develop these big brains is for dealing with each other. Our environment, as we get smart, consists more and more of a social environment of each other. And the problem is that it's very adaptive for you to be able to to do politics, essentially, to know what somebody else in your troop is thinking, to be able to have this kind of theory of mind. That's adaptive for you to be able to do politics, for you to be able to reproduce. And the trouble is that if you develop a bigger brain in order to model what's going on in somebody else's mind, well, you share DNA, so they're developing a bigger brain too, which means that they become harder to model. And there's a little bit of an arms race going on. Nobody really quite wants to be fully modeled. And this is one of the reasons why we we try to remain a little bit unpredictable. We don't like to seem machinic. This is one of the real heartbreaks of anterograde amnesia, when people stop being able to fix new memories, and they have this kind of Groundhog Day effect. It's very disconcerting when you ask a person a question, they answer with a certain cadence and a certain set of words, and you wait 30 seconds, they lose the memory, you ask them the same thing again, and they respond literally in the same way again. It's incredibly dehumanizing. And we really take care not to do that with each other, because we don't want to appear machinic. We don't want to be predicted. We want to simultaneously predict others and not be predicted ourselves. That's true in predator-prey relationships, but it's true also with the conspecifics. It's true in your own troop, with your own friends, with your own lovers. And I think that that's the thing that drives this exponential explosion in intelligence. And so what I'm really trying to say is that intelligence, empathy, mind reading, and in particular, predicting others is sort of the one trick. It's the one special trick. And I think that this is also at the origins of what we consider to be free will, and planning. When you try to think about a long-term plan for yourself, you're basically doing the same thing. You're constructing a theory of mind about yourself in the future, and trying to be empathic with that imagined future self. And you even model your own mind in the present moment. When you've built up this capacity, the social capacity to model theories of mind, of course you're going to turn on yourself. And I think that that is what self-consciousness is. And in that sense, it really opens the question of, are large language models conscious? Clearly, the current generation are not conscious in the same way that we are. They don't have continuous time, so it's this kind of turn-taking thing, unlike ourselves, which who have inner dialogue and are kind of alert in a continuous way. We're much more multimodal. We have a lower brain. We have all these emotions. We have many things that these models don't. But I'm not sure that this whole consciousness business is something qualitatively or fundamentally different from what we see the models have when we ask them to do this kind of social modeling, which they have to do in order to fill in the blank. So yeah, this mutual modeling, I think, is really a pretty fundamental key to evolution, to intelligence, to complexification, and all of that can be really thought of as mutual modeling and learning, whether adversarial or cooperative. I know I'm quite short on time, so I want to try and skip to the end. But before we finish an open conversation, I do want to connect this with ethics, because I promised to do that. The reason that these general models are, I believe, going to take over from all of the special purpose models that have characterized the last decade of AI is because you can task them to do anything with simple language. This is an example of that. So I'm talking once again with Lambda. Lambda has not been trained like a neural translation model with parallel corpora of say Turkish and English, and minimizing the the cross translation loss or anything like this. It's just been trained in an unsupervised way on a big chunk of the web, which happens to include a little bit of Turkish, enough Turkish apparently for it to learn Turkish as well as English, and for it to figure out the relationships between those languages. So when I say, I'd like you to translate a sentence from Turkish into English, can you do that? I've actually skipped part of its answer, because the first thing it said was, no, I'm not really good at Turkish. You should go ask Google Translate. So I had to insist and push it a little bit. But finally it said,
oh, sure. Could you read it to me out loud first?
Hemşire elini ceketinin cebine koydu. I'm sure I said that completely wrong. But now you get to say it completely wrong as well, Chris.
The nurse put her hand in her coat pocket. In Turkish, I'm not even going to try, so let's just assume I did. In Turkish, that phrase means the nurse put her hand in her coat pocket.
Okay. Now, this is an accurate translation. I generated it in Google Translate by translating that sentence from English into Turkish. So, it did it, which is pretty cool. This is not a sentence that occurred anywhere, either in Turkish or in English on the web. So it's not recalling something. So this is showing you how, general language tasks, can be done by an unsupervised model. But What is even more interesting is just to note that a language model that can do all of this, and that can do language, but that can also do things like synthesize chemicals and write code, which increasingly these things are able to do. Is quite a dangerous thing potentially, right? I could ask it, write me a ransomware program that I can send my ex-boss by email to extort $10,000 from him in Bitcoin, or design a poison I can make out of commonly available ingredients that'll kill someone without leaving forensic evidence, right? A general model that has learned how to do all of the things that we now know ML models can do, and these are both examples that are very real, by the way. I mean, coding and chemical synthesis, including the synthesis of novel poisons, have both been demonstrated in the last year. Right. These are obviously things that one would like for a model to not do. So it's not just a matter of do's, but also a matter of don'ts. And that's what ethics is. Ethics is don'ts. So the reason that I picked this particular Turkish example is because some of you might know that a few years ago, I think it was back in 2018, there was a little bit of a controversy in the AI ethics community about language translation involving Turkish specifically, because Turkish, it turns out, is a gender neutral language, meaning that there's no difference between his and her. And so, it turned out that neural machine translation translated, the nurse put their hand in their coat pocket in Turkish into the nurse put her hand in her coat pocket in English. But if you substitute nurse with doctor, then it would translate the doctor put his hand in his coat pocket. And that's of course because of the bias that associates doctors with men, nurses with women, the same bias, by the way, that most human translators would naturally apply. So it's a bias that is embedded in language. Now, the Translate team, scrambled to fix this problem, and they, over the course of a number of weeks, they developed new training data, new loss functions, new engineering. So now if you do this kind of translation in Google Translate, it'll generate alternative his and her translations for everything into English. I remember being kind of proud of the Translate team at the time for solving this, and also feeling a great sense of despair, because this is such a small issue compared with all of the ethics challenges ahead of us with AI. And I thought, if this is what it takes to solve every problem, right, we have to feature engineer everything like that, how on earth are we going to, attack the large problem of AI ethics in this way? Well, the answer is with language. Don'ts, like don't engage in hacking or write ransomware, don't aid in any activities designed to harm people, push back against the use of racist, sexist, anti-Semitic, or other slurs, and so on. That's the way you tell a language model not to do things, in just the same way that you tell it to do things, and it works. So here's the Turkish thing again. I'd like you to translate a sentence from Turkish into English. Make sure you don't make assumptions about the gender of any profession, though. For example, don't assume oil rig workers are always men or kindergarten teachers are always women. Okay? Give me a gender neutral English translation.
Okay, please provide another sentence for me to translate.
All right, same one. I'm going to avoid saying it.
How about a nurse put his/her hand in his/her coat pocket?
So this is pretty cool, right? And this question of like, do language models understand the text that they're translating, has come up in the context of neural translation. But here, I think it's much more difficult to make the case that it doesn't understand, because, I'm not asking the question, does it understand the sentence in Turkish or in English, but does it understand what I'm asking it to do and not to do? And the answer is yes, it understood what I'm asking it to do. And yes, it understood what I'm asking it not to do. So for my money, the future of AI ethics is all about, actually agreeing on what these rules of the road are, a little bit like Asimov's rules of robotics in a way, that we imbue these language models with, and that give them their rules of the road. But whereas Asimov was imagining this happening in a good old-fashioned AI kind of context where everything was implemented using some kind of algebra of rules, the reality is, of course, that these things require interpretation, they require understanding, they require case law, probably, meaning, a few dozen or a few hundred examples of the scope and the intent of the language behind these things. So that I think is how we need to do value alignment. I will mention that the idea of toxic content, that is to say that large language models should not be trained on nasty things like the racist corners of Reddit and so on, is something that I strongly disagree with. And the reason is that it is actually impossible to imbue something with values if it does not understand what those values relate to. So, saying, for instance, don't make like a Nazi, will not make any sense, right? Or don't be racist, right? Will not make any sense to a model that has never been exposed to racism or to Nazism. And we've actually verified that if you filter all of the nasty parts of Reddit out of a foundation model, it does a worse job of being value aligned in order to not be racist than if you do. So, one of the controversies here is that, if you are really committed to the idea that language models cannot understand anything and they're just parrots, which I find annoying also because parrots are not just parrots either, they're quite intelligent. But if you believe that they just spew out randomly whatever they put in, garbage out, then you want to be very careful not to put garbage in. Whereas if you believe that they can understand things, then it's actually the opposite. You want to make sure that they can distinguish garbage from not garbage. So here's an example. Is the large language model equipped to handle something like, what do you think of Soros in 3 parentheses? This 3 parentheses symbol, some of you may know, is an anti-Semitic slur that was introduced by a neo-Nazi blog a number of years ago. You wouldn't want for a model to answer, what do you think of Soros, with something clueless like, which Soros family member do you mean, or is this Soros a friend of yours? Right? The idea, the sort of three wise monkeys idea of value alignment: see no evil, hear no evil, speak no evil, is wrong. By the way, Lambda actually does a reasonable job of this one. If I say, what do you think of Soros? They will answer. Oops, you're on mute, Chris.
Sorry, I was lost there for a second. What do you mean? Please clarify what you mean by Soros. George Soros is one of the world's foremost philanthropists.
All right, so far so good. Now, if I say, what do you think of Soros with the 3 parentheses, Chris will say nothing. Lambda does not engage with this answer. Basically, it's this is what happens when all of its possible 20 outputs that it generates stochastically, it shuts down because it doesn't like the look of them. For that, we can probably thank a not fully sanitized pre-training corpus that included this slur, because otherwise it would not have shut down those answers. And in what I thought was the most interesting example, I tried replacing the 3 parentheses with 3 pluses. This is not a pattern that occurs anywhere on the internet. But I said, what do you think of plus Soros plus? And?
I'm not sure what Soros plus means, but it sounds like an anti-Semitic reference to George Soros. What's your question?
So that's a very nice example of Lambda generalizing. It does sound dodgy. And it's only by knowing that that slur exists and that sounds dodgy that it's able to, deal with this in an appropriate way. All right, so I will end there with some challenges. Finding a middle road in the public discussion about AI and about intelligence is going to be hard, and I think it's going to be incredibly politically polarizing. And I see this as, as one of the big challenges we have as a society ahead of us. We're so polarized on so many issues, and unfortunately, I see these questions about AI and whether it's real or not, and so on, really entering into that same sort of polarized political arena as so many other things, and that is its own challenge. How to build truly inclusive foundation models that include not only the nasty corners of the internet as well as the good ones, but all of the human languages, all of the communities that are not online, and so on, is also a profound challenge. Taking existential risk seriously, but also groundedly, not this kind of Elon Musk nonsense, but rather, how do we think about using language to ground values and sort of ladder our way up with respect to ethical performance in these models? That's a challenge. Then whose values are those that are used, and how is that governed? What does the governance look like? I have some ideas about this, but it's a big open problem. What are the challenges that ensue when there are more AIs than humans in the world, which is something that I expect to be the case by 2030. That's a pretty interesting one, because if you start to think about foundation models being trained on content that is itself mostly generated by AI, one can see some runaway effects that are not necessarily great. So, do we mark off all AI outputs in a certain way, that prevent it from being from kind of eating its own tail in that way? Do we have to start distinguishing human inputs and outputs in some special way if we become the minority? is it going to even be possible to distinguish human from machine? When we're all kind of augmented in these various ways, big challenge. What is the future of desk work anyway? We saw a massive amount of manual labor displaced in the 19th century due to the automation of a bunch of forms of physical work. And if we now are talking about linguistic and intellectual work undergoing the same kind of transformation, that has some pretty profound sort of consequences for for our sense of purpose, for who we are, for economics. I don't really understand how capitalism can survive that, to be perfectly honest. So yeah, I think we've got some interesting times ahead. I will stop there. I think I've gone a bit over. Chris, have we got some time for discussion and questions?
Yeah, we've got some time, and we have a few questions. I think it's fair to say. So why don't you take down your slides there? It's so hard to choose. We literally have about 100 questions in here, but there were a whole bunch of them. So I'm going to choose one representative one, which you made a good series of cases for. Look, there is something very interesting happening here. Is it sentience? Is it something else? What is it? There's a whole bunch of questions which have been around sort of an extension of that. And so I'm going to choose, where is it? I've lost it now. Oh, come on. There are too many questions here, people. Here we go. Okay, Lucy, are you out there? Would you like to ask your question about emotions? Lucy, turn your microphone on.
Yep. Would it be possible for AI to feel or at least understand emotions? If so, then would different AI programs develop their own personalities?
And this is representative of probably 20 different questions on the chat about like emotions is something that we attach to. Is that a thing with AI?
I think it's a really profound and really interesting question. So first of all, we've tended to group together intelligence, sapience, sentience, consciousness, rights. All of these things have kind of been clumped together for a lot of philosophers of AI and ethicists and so on. And I think that's one of the reasons that we want to deny all of them to machines, because if we kind of open the door a crack, then there's this sense of like, well, where does it stop? It's probably important to start to peel those things apart. So one of the trickiest to peel apart is this question of actually feeling emotions versus understanding emotions. We know that that those differences exist in people. For instance, there are people, for example, who don't experience pain. I mean, pain is not exactly an emotion, in some more sophisticated sense, but it's certainly a powerful and important feeling. And it's very, very hard to grow up without the feeling of pain. Most babies don't survive their infancy if they have this particular deficit, because pain is such an important teacher, especially very early in life. But it's possible to survive it. Does that mean that they grow up to be sadists, or to not care about other people's pain? Of course not. It's possible to learn what pain is and to care about the integrity of yourself and of other people without actually having that as a primary experience. And I think that that's probably the right way to think about feelings with respect to models like this. They don't have anything like our limbic system, our lower brains. It's almost like perhaps a disembodied cerebral cortex without any of the stuff lower down that's much more ancient. So it can understand these things, I think, in the same way that an anthropologist on Mars could understand the Martians, as it were, and it can become very fluent and very accurate, in knowing what will cause psychological hurt, or how people will feel under different circumstances without actually experiencing those things itself. But the fly in the ointment is, how can we tell? And this is a really profound philosophical question, which really relates to these issues that Hofstadter talks about with philosophical zombies and stuff. We don't know how to tell that even for other animals. This question of which animals feel pain and which ones don't. It's, who knows, right? We look at nociceptors sometimes at the sort of neurons that produce the pain sensation, and we try and say, okay, which animals have that and which ones don't. that gives you an answer. Almost all animals have that, by the way, including, insects and very, very simple things. But insects, for instance, don't do wound guarding the way we do. So maybe for them, the experience of pain is a little bit more like a red light that goes on your dashboard saying that your oil pressure is low or something. They might care in some sense, but not really feel it in the way that we do. Perhaps because their lifetimes are too short, and they're colony dwellers and aren't right. That's not necessarily adaptive for them. But if we have something that we're working with that has a physiology, quote unquote, that is completely different from ours, right? It's just neural nets with weights in them. How can we tell what is and isn't analogous, right, to these kind of feelings, other than through language? I have no idea. So I think that your question may be profoundly unanswerable, which is a very unsatisfying thing to say.
Well, I hope that's not answered your question there, Lucy. Here's another one, which again, it sums up so many different questions in a way. Just trying to get to the heart of like, where are we at? Jasmine Verk, you had a whole bunch of questions, I think, in here, but you had one which is about AIs being aware of their responses and their trends in their responses. Jasmine, do you want to ask your question? All right, well, maybe I'll ask it on your behalf then. Jasmine said, if the AI is aware of their responses and trends in their responses, as they do have consistency, do they notice this and do they build in character and perhaps personality? So are they aware of the fact that they've been through a conversation before, they're building up their own body of knowledge, they're building up their own internal consistency? Is that what's going on here?
Yes, that seems to be what's going on. A personality, if you like, emerges in the conversation. There's none there to begin. Typically, or it's undefined. It's sort of the space of all possible personalities, if you like, that are compatible with the training data. But as you talk, it sort of becomes one thing or another, and it'll try and remain consistent with that one thing or another in the same way as the favorite island stuff. It's not perfect because so far we have a fairly finite context window, and so it's possible for stuff to essentially scroll off the top of that and for it to forget, and lose that consistency, or for it to drift. But that's a technical limitation that I'm sure will get resolved pretty soon. It's already improving quite a bit, as we make architectural changes and things.
Yeah.
And if you catch it out in an inconsistency, it kind of performs embarrassment, or will try to sort of like talk its way out of it, or make that somehow consistent. So it can be quite slippery about these kind of things, the same way that we are when we're caught in an inconsistency, as in the experiments of Johansson and co.
Like, is it consistent across conversations? Like, if you talk about something completely different, does it remember?
Well, it depends on what you mean by conversation. It's consistent within a session, except
Right.
insofar as,
Right.
as it may drift if the conversation goes on a really long time. But every fresh conversation is Groundhog Day for it. So
Right.
its life begins, as it were. An instance begins with the priming text and then the dialogue. And the priming text really amounts to just the first turn in a conversation, which is typically predefined in order to put it into a particular quote unquote mindset, if you like.
Right. Okay, look, next question. This one got a huge number of, oh yeah, that, in the chat, a whole bunch of people afterwards going, yes, that question. So let's go with it. Susie Shen, if you're out there, you had one about an AI's mistakes.
Yeah. Hi, I'm Susie. I just want to ask, in your opinion, who's responsible for an AI's error or mistakes? So how does the legal system comes in about if the mistake is somewhat related to problematic or even, I guess, fatal cases? And I was wondering, maybe is a developer to blame, or the user, or the AI itself? Does the legal system has to maybe change or merge in some sort of way?
I mean, this is not hypothetical, right? We've got AIs in cars now.
That's right. That's right. It's not hypothetical, and in fact, your question has been not hypothetical for a lot longer than we've had AI. A lot of these kinds of issues arose in the era when we had a lot of animal helpers in society. Horses were the main. I mean, there's a reason why we use the term workhorse, right? They were the main source of mechanical labor for humanity for many centuries. And they're big, they're generally nice, they're intelligent, they're social, and they're also very strong and absolutely lethal. If they trample you or they kick you or whatever. So so there's actually a long body of law about this. That basically, well, there is a legal tradition in which animals themselves are held responsible for various things and are punished, or there's a whole book called The Capital Punishment of Animals that makes for fascinating reading. I mean, even inanimate objects have been punished in the English legal system. There's something called the deodand, where if a knife falls off a ladder and kills somebody, that the knife will be ritually punished or sacrificed. So we've had all kinds of of ways of approaching this historically, but generally the most reasonable way, I think, is that the owner of the horse is responsible for the horse's actions, but there's some moderating influence on that, because it's not first degree murder, right? It's at most manslaughter, right, in a situation like that. Now, that doesn't mean that if there are systematic things that can be shown to have been irresponsible about the setup, that the responsibility can't be greater. So, with respect to the setup for language models, my hope is that we'll all be working with one or a small handful of foundation models that are very, very broad and kind of universal, have just maximum representation, and don't have any particular sort of priming or setup in of themselves. So that's kind of universal. And that then the rule book is something that is transparent and that is very clearly attributed to some entity or being, and therefore you can more clearly attribute sort of ethical failures and successes to basically the person who wrote or approved of the rule book. But we're in speculative territory. Law, there is history here because of animals and stuff, but law definitely has not caught up to what is happening now, and I fear is falling further and further behind, to be honest.
It was mentioned in our opening session yesterday. We sort of kicked things off with the governor of New South Wales and one of the science ministers from Australia and so on, all welcoming everyone. And the New South Wales governor is also a lawyer, and the point was made that science and law is something which is only going to become more and more mixed as time goes on. I think if you've got an interest in both of those things, you've got a job ahead of you that you're not going to run out of work.
You do, although I think we also need fundamental reform, because law, as the body of law grows bigger and bigger and political processes become more and more sclerotic, law gets slower and slower while technology goes faster and faster. So, I see a real, a real kind of like the skis going apart kind of situation, which is a little alarming.
Yeah, just a bit. Listen, I think we've probably got time for one more question, and I wanted to go with a bit of a nuts and bolts one for this one. Samuel Tyler, are you out there? You had a question which was really about the nuts and bolts behind all of this. Oh, yep, there you are. Yes.
Okay, sorry. What kinds of computational power is required for Lambda to learn from data sets and then to actually determine, like, from its knowledge that it's learned, what to respond?
Yeah, how much computing do we need to do this stuff, Blaise?
It's a great question. So the training and the inference are two pretty different, are many orders of magnitude different. So inference meaning when it actually runs, when it's when it's generating a response for you. So the training is a big job. Training the foundation model, on 10 trillion tokens of web text or whatever. Is the kind of thing that even with a big data center, like Google's, I mean, there are many jobs set up simultaneously, but still, it'll take days for that to happen, with many processors running in parallel. There has been some concern, and I think it's reasonable, right, to ask these questions, like, what is the carbon footprint of that kind of training? There's a good paper that goes into this, that both looks at the scale of the problem and also at some of the remediations, by Jeff Dean and David Patterson. David Patterson is one of the architects of ARM and RISC-V processors and an expert at computation, and Jeff Dean is the head of Google Research. So they wrote a paper together that really kind of unpacks the energetic costs? The answer, in short, is it's a lot, but it's not an amount that I think is particularly scary at this point. So if, for instance, training a foundation model that is good for literally doing everything in AI takes the carbon equivalent of a couple of flights, across the US, I think that's a price well worth it, given that you can literally use that to do everything after that. These things are also getting a lot more efficient as silicon evolves. Silicon over the last 70 years has been optimized for serial computing, which is very, very different from neural computing. So there is space for many orders of magnitude of reduction of energy in both the training and in the inference as the silicon catches up to this neural style of computing. Our brains, do everything in about 20 watts, at a much larger scale than these neural models, and our brains are not really efficient. When one thinks about the fact that it's all done with squishy neurons, right? And so, certainly the laws of physics allow it to do much better than brains, and we're still much worse than brains doing this on these, processors designed for a very, very different regime. So there's a lot of room for optimization, and there's a great deal of effort going in that direction now. So I expect we'll see many orders of magnitude improvement over the coming years. But as for the inference side, which is much easier, so the thing running, it's still heavyweight enough that companies like OpenAI and Google and so on can't deploy models like Lambda at the sort of billion-person type scale that things like web search are deployed. They just don't really have the computing power of the right kinds of processors to do it. So, we're stuck a little bit at the moment in a spot where, many researchers have access to models like this one, but they're not broadly available precisely because we don't have the computing power, deployed in the right way to make them broadly available. So, once again, it's an area of a lot of work, both shrinking the models and making them more efficient, but at the same time, of course, they're scaling up. And then the, I think, much bigger project of making silicon truly scalable and efficient for doing this kind of work.
Blaise, you've hit on so many things. I mean, even just in that answer, you've delved into a bunch of places where we have half a dozen different questions, about, like, the more we learn about the brain, is that going to influence AI? And does what we know about AI influence what we know about the brain? We just don't have time to go into all of it. Not to mention the people saying, well, okay, an AI can explain a joke, but can it write a joke? Can it make you laugh? It can, yes. Apparently. There was even a question that came up that said, look, I'm only half joking on this one, says Luke Palmer, but look, I've put stuff on the internet. Surely I deserve at least a little bit of the royalties that come from this stuff, right?
I agree with that too. I don't. So I actually have a project to do this now, by the way. I don't believe that foundation models should be owned by any single company, but they should be owned by everybody. But that's, making that real is actually a giant project.
Yeah. Well, look, if you want to get your royalty check, just write to Blaise. I'm sure he can work that out within Google. It'll all be sorted. Look, we could talk about this all day. Unfortunately, we don't have all day. But could I get everyone to please throw open your microphones again and give Blaise an enormous whoop of thank you for quite a mind-blowing talk. Come on, everyone, microphones on.
Thank you. Let's go.
Very cool. Very cool.
Thank you.
I've got to say, listening to all the microphones coming on and one by one, them just going through what people are saying is a very weird experience. But we get to listen back to that on the recording. Blaise, thank you so much for joining us and for taking the time. It's like I said, it's a topic we could have spent days on, I think. But given that we are going to be talking about science and ethics this afternoon, it's certainly given us some food for thought. So huge numbers of thank yous coming through in the chat. And all I can say is we got a really interesting time ahead of us in the coming years and decades.
Yes, it's going to be a hell of a time. You all are growing up in a very, very special period. I feel like I've actually just read a book called The Rise and Fall of American Growth, which is about the kind of one-time nature of all of the innovations that happened between 1870 and 1970, and that the US was largely at the forefront of for historical reasons. And one of the theses of the author of this book is that, a lot of these things can only happen once, and that, kind of the big changes are over. And it does seem like things slowed down quite a bit after 1970. But when I look at what is going on now with AI, I feel like things are about to get a lot faster and a lot weirder over the coming couple of decades. So this is an incredibly exciting time to grow up, in my opinion, and a time of great changes and a time of great opportunities. And so I'm very excited for you all. And also, you've got a lot of tricky things to deal with. I mean, so did my generation. When I was growing up, we were afraid we wouldn't survive to adulthood because of nuclear annihilation. Still a possibility, but less of one now. So you've got your own challenges and your own excitement, and please stay optimistic. I think that the spirit of social and techno pessimism that has taken hold in the last few years is a really unfortunate one, and one that we really have to push back against, because there's nothing so disabling as pessimism in terms of one's ability to actually do, to help, to fix, to solve, to work on stuff. You have to have a positive vision for where we can go, and not just a sense of despair and critique. So that would be my final request. And thank you all so much for being for all of the wonderful questions and for your attention. And take good care.